Chastity Reed. Peter Postma of FilmLight gave an incredible presentation at the May 2009 LA Red Users Group gathering. His talk on color management was quite an eye-opener.
And actually what's more important is the dynamic range or the contrast ratio of a display device. One way of measuring that is just put up a black patch on the screen, put up a white patch, and measure the difference. So if I have a 16 foot Lambert white and a 0.01 foot Lambert's black, it's a 1600 to 1 ratio. My contrast ratio is 1600 to 1. So that tells me kind of how good my digital display device is doing. You can also measure it with a checkerboard pattern like this, because the white patches will invariably bleed into the blacks a little bit, and that will lower the contrast measurement. Or you could do it the way manufacturers do it, where they wave a magic wand and put down the biggest number they feel like putting down. And they do all kinds of tricks, like measuring the chip in a projector without accounting for the lens or the screen. They'll put a monitor at its darkest setting, measure that for black, put it at its brightest setting, measure that for white. It's all kinds of things they do. So you can't trust a contrast ratio that's just in a spec sheet. You actually have to measure it in the environment that you're going to use it in, and that'll give you an actual, reliable contrast measurement. So I'm going to show you some curves that kind of show why this is important. If I consider an LCD monitor calibrated to standard computer specifications, sRGB, HD monitor calibrated to 709, HD standard specifications, and a DCI reference projector, they do all have slightly different gamma. The yellow LCD here is 2.2. The DCI reference is 2.6. But if I plot the actual luminance of these devices, you'll see the biggest change is the brightness. A standard LCD monitor is much brighter than a CRT monitor or a digital projector. But these luminance measurements are linear, and the human perception of light is not linear. We're much more sensitive to changes in the shadows than we are to changes in the highlights. So if I count for that fact, the perceptual luminance, how we actually see brightness differences, the biggest brightness difference actually isn't in the high end here, it's in the low end. It's the fact that this LCD is only getting down to 0.126 foot Lamberts, whereas the digital projector can get down to 0.08, and the CRT even darker to 0.06. And again, if I'm looking at the LCD in bright office lighting conditions, and the HD monitor in HD reference conditions, and the CRT in black conditions, the actual white difference all gets normalized out, because our eye adapts to those different view environments, so it'll look as roughly the same brightness when we go from room to room to room. And so when I do that, you can clearly see that, yeah, the shadow differences here are really what's going to cause me problems when I try to make one display device look like another. So if I have an LCD with a 450 to 1 contrast ratio, and I want to try to make it look like a CRT monitor, I'm going to have problems because I just can't get a good black that matches what the CRT can do. Again, you can do tricks in color management to try to make sure you have the same amount of shadow detail, to try to compensate for some other stuff, but eventually you hit the limits of what that display device is capable of doing. So that's why the contrast ratio is so important. It tells you if you're going to be able to get the same dynamic range as what you're trying to emulate. So if you're trying to emulate a film projection, you need a projector with at least 1500 to 1 contrast ratio, preferably more. Otherwise, you're not going to have any chance of having it look like film, even with all the best color management in the world. So the other problem you often run into is a color gamut issue, where you could use a pretty simple 3x3 matrix and a gamma function to make two colors match. So if I have a color on a digital projector, I want to get the same color on a CRT monitor, I use a certain percentage of red, green, and blue on the projector, and a slightly different percentage. I could calculate what I need in my CRT to match that color, and they'll look exactly the same. Eventually, they'll all hit a color like, say, this saturated red, and if I put it through a matrix and gamma function, I need 170% red and negative 14% green, and that's impossible. I can't push my red any higher than it already goes, and I can't suck green light out of the room. So it's kind of the color science equivalent of this. The only thing I could do is clip the colors. I could get 100% of red, I could go 0% of green, but now that's not the same color. They don't match anymore. It's clipping. And when you look at the CIE diagram, you can clearly see why that is. This green triangle is all the colors that the DCI reference projector can reproduce. The red one is one's a standard 709 monitor we can produce, and I'm trying to get a color out here that just doesn't exist on that 709 monitor, so it's going to get clipped. And this is what it looks like. So this is an image that was mastered on a digital cinema projector. And right now I'm just taking those same RGB values, adjusting for gamma, and putting them on my HD monitor. So it looks kind of washed out and less saturated than it would on a digital projector. If I apply the LUT, the matrix and the gamma LUT to make those monitors match, this is what the DP and the cinematographer actually wanted, was this kind of warm flesh tone. But you see I'm now losing detail in this flower because those reds are outside. Yeah, it was actually more intense on a digital projector. I can't show you how intense it was on this monitor because it's reached the limit of what this monitor can do. So you can do more advanced color gamut remapping to kind of manage these colors and try to make sure they don't clip or clip in a way that's less noticeable to the eye. A lot of systems will also have a gamut alarm like this, which turns everything black and white that will be exactly the same on the two display devices and leave in color what's going to be different. So clearly, if a colorist got into an image and it looked like this, they could turn on the gamut alarm and say, okay, that's actually the limitation of my display device. It's not an artifact in the image or something like that. So I only have a few more minutes, but I'll real quick go over a common question I get, which is what's the difference between a 1D LUT and a 3D LUT? A 1D LUT is basically just a set of curves, one for red, one for green, one for blue. So it's actually three 1D LUTs are used, and they can adjust contrast, they can adjust white point, but it gets really tricky if you want to adjust individual colors. For that, you need a 3D LUT, which actually looks at the entire color space as a whole rather than just the red, green, blue channels. So say I was in this situation where I wanted to make this red look like that red, I could adjust my red 1D lookup table, but as soon as I adjust the red LUT, I'm now affecting orange, I'm affecting magenta, I'm affecting yellow, I'm affecting all reds, I'm even affecting gray because those all have a little bit of red in it. So if I want to affect just the red without anything else, I need a 3D lookup table, which then models the color in 3D space with green on one axis, red on one other, blue on the other, kind of gives the full spectrum of color, and I can individually move around any of those points in the color space to where I want to. So say for film emulation, this is the best I can do with a set of 1D lookup tables. I could get the contrast looking right, but these color patches, the Kodak logo and stuff like that, are much brighter than they would be on film. But if I make them darker, it makes the whole image darker, and that just doesn't work. A 3D lookup table can properly manage all the colors, so this is what the image would actually look like on film. The colors will look more deeper and saturated, but the contrast and everything is still correct. And the neat thing about a 3D lookup table is that it can represent any color transform no matter how complex it is. So any color transfer going from one set of RGB values to another can be all compiled and stuffed into a 3D lookup table. So it's a really powerful way of doing all sorts of different color transforms. The only thing it won't do is a spatial transform. So if I want to do like a power window or a shape over just one area of the image, 3D lookup tables don't have any idea what the actual image is. It's just applying the same transforms to all pixels. But apart from that, you can put anything you want in a 3D LUT, so it's really powerful. And then just as a practical matter, if we actually tried to keep track of every single possible color in color space, we'd run out of memory on most computers. So what's actually done in 3D LUTs is you have kind of a lattice with a bunch of points on each axis. And when you go to apply the LUT, you just interpolate between that lattice to figure out how to change your color values. So in practical point of view, you can use a 1D LUT to do some larger changes and a 3D LUT to do the more subtle changes. And then a cube with 16 points on each side or 17 points on each side is more than enough to do most color changes. So that's pretty much my presentation. Are there any questions?
The LA Red Users Group meets monthly at Kappa Studios in Burbank. From Hollywood, I'm Chastity Reed.